Okay, so today we will be covering two of the fundamental dictionary techniques. Actually, we have seen one of them already. It was LZ77, if you may remember. This was covered. LZ77, this was covered. And it was just looking at the past of the information, and from there, from the past, uh, it was looking at how much of the future samples or pixels or whatever have already appeared in the past. And then it was just making a representation of the data as go back this much and copy this much. So it was like this. If there is X, Y, and Z that is happening right now, instead of representing these X, Y, Z's, it was looking at the past and if X, Y, Z appeared before or not. And then the two representations were how much to the past you have to go, let's say A, and then how much you have to copy, let's say B, which is 3 in this particular example. So the representation was A and B. Go back this much, copy this much for the new representation. The new technique that we will cover today, which is the last thing that we will be talking about in the dictionary techniques under the topic of dictionary techniques, is the LZ78, which was implemented or discovered 1 year later. That's therefore that is the name. That's where the name comes from. So Lamplziv 78. Now this one is a dictionary, more like a dictionary technique instead of a lossless compression technique like LZ77, and this is why Lamplziv techniques are usually considered under the broad topic of dictionary techniques, because it literally makes a dictionary, and it's again the best to see how it works over an example. The example that we will cover is this. Let's say the text, the letter sequence that we will encode is, let's say, A, B, B, C, B, C, A, B, A. And as you will see, if the examples are short examples like this one, usually the efficiency is not visible. Such techniques become efficient for longer sequences, because in longer sequences, repetitions start to occur. So this is just, I mean, I don't know, 9 bytes or something. If you try to compress a 9-byte text with these letters, if you try to zip it, you don't really get anything below 9 bytes, actually. But anyway, the idea is important here, and you will see how or why it should be working well. In step 1, we have a position counter. That position counter is automatic. We don't really keep it, but this is the dictionary that we construct. It's like the multi-front technique in a sense, which requires bookkeeping of a dictionary. In position 1, the first thing that we incorporate is the first letter, which is not in the dictionary, which is A. So the output that we will do, by the way, this is the dictionary, and this is just the position that we have. The output will be, we don't copy anything from the dictionary, that is a 0, and then we output A. So when this symbol or the set of combined symbol is observed in the decoder side, the decoder will also automatically insert this A into the position of 1 into its own dictionary. Therefore, the decoder is also constructing the dictionary. It is symmetric, and the utilization of the dictionary from the encoder side and the decoder side will be symmetric. Therefore, this is a decodable code generation. In the second position, there is B, because the second letter is B in this example. So we don't copy anything from the dictionary, and we emit a new symbol, which is B. So the decoder is also incorporates B into the second position in the dictionary. And then in the third position, we emit something like this, and it also automatically produces the dictionary. We are in this position. We are here, actually, B, but I will encode BC because B is already in the dictionary. So I don't need to try to transmit that information again. Instead, I will write something like this. Go to the second position of the dictionary, copy it, and then the new symbol that we have, which overall in a combined form doesn't exist in the dictionary, is because of the C. So I transmit C. I transmit 2 and C. So the representations of the first parts and the second parts should be different in a sense. By the way, I'm not talking about the implementation. The implementation, of course, does not require the use of parentheses, the commas, and everything, because they are also bytes, 1 byte long. It doesn't work that way. It's just a pair of bytes or something like that. The first byte corresponds to what is the thing that we are covering, or the first bits, some certain bits, is a numerical entity. The second is just a character. So 2C is, in a way, I'm not telling how, but in a way, transmitted. And that makes a new dictionary edition. But notice what that dictionary edition is. It's a combination of the previous element in the dictionary, which was at position 2, it was B. And then comes C. So BC in a combined form is now added to the dictionary. And when the decoder decodes this one, it also automatically puts BC to its own dictionary. So the dictionary up until now is the same for the encoder and the decoder side. And then we are in this place. Now you see that if you look at B, it is in the dictionary. If you look at BC, it is also in the dictionary. And if you look at BCA, it's not in the dictionary. So it's BCA that we are trying to construct right now at the position 4. The position is not critical, it's automatic, as I say. So the output I will make will be 3, which corresponds to BC in total. And then we have an A, and the dictionary becomes BCA. The dictionary also becomes BCA in the decoder side. So all of a sudden, we just encode these things. And then I arrive here, which is B, which is in the position of B. B exists in the dictionary. And then I check even further, I prolong it as long as it is okay. I look at BA, and BA is not in the dictionary, so I write it like in the 5th position, whereas BB is at position 2, and after that comes A, like this. And I have to include this now into the dictionary, BA it becomes. So as the dictionary is becoming more and more long and complicated, but its representation, so these entities start becoming longer, and their combined representations are just according to the position numbers, which are just 2, 3, etc. So this is how the LZ78 algorithm works. This thing is slightly less efficient than LZ77 in terms of compression capability, because it's looking at the dictionary only. It's not looking at the whole past. And if something is just constructed and put into the dictionary by coincidence, or sometimes because you don't put just everything into the past dictionary, but it appears in the past. It may appear, there's more chance to find something that appears in the past, because the dictionary is fragmented. It is constructed on the way, but it is fragmented, and some things of the history is not put into the dictionary. The dictionary covers a summary of the past, okay? But um, despite its inefficiency in terms of compression efficiency, actually it is very efficient in terms of memory efficiency, because the dictionary is shorter than taking a look at the past. For example, when you arrive here, you look at the past by 1, 2, 3, 4, 5, 6, 7 deep, 7 characters deep. Whereas when you are here, you look at 4 dictionary elements. Excuse me, 4 dictionary elements deep. Usually, therefore, looking at the dictionary is more efficient in terms of memory and in terms of computations. But in terms of finding what exactly is happening, which is the efficiency in terms of compression, well, LZ77 works slightly better. And that is why this method of LZ77 is again considered after the successful speed up of the computers. In the old days, the computers were not capable of running it in a reasonable runtime, because it was a little bit complicated in terms of memory and computation efficiency. But now the computers are fast, so it's possible to use this one instead of this one. Although LZ77 is the older one, it is nowadays used more. But that essentially concludes the discussion that I would do for considering the lossless compression. We haven't seen many things like we didn't see the LZW, sorry, LZW. We haven't seen Golomb and Rice codes. What other things that we didn't see? Well, if you take a look at the book by David Salmon, basically, you will see that the chapter dedicated to lossless compression is quite comprehensive. And every time you make some small adjustments to the algorithm, you give a different name. But the idea of the dictionary techniques, the idea of run length coding, the idea of Huffman and Shannon type coders, the idea of arithmetic coding, those are the significant, critically different algorithms that we would like to cover. So that's what we have seen. And right now, I want to stop the discussion of the dictionary techniques, and I will proceed into a new stage in the compression. Remember always that the compression systematics consists of typically 3 stages, where the first stage was the transformation or the prediction, which reduces the entropy or the energy content of the input data. And then there is quantization, which converts real data into indices, indexes, integer indexes. And those integer indexes are finally compressed by lossless compression techniques that we have seen. Sometimes we don't need the signal, we don't need quantization, because we are not interested in lossy compression. So we directly apply the techniques for lossless compression. It's usually for text data or for executables, or even sometimes for biomedical signals, which desperately require use of lossless compression. So they are there. We don't use the other sections of the compression, but in general, we use, for a majority of signals, we use all three of these compartments. So we will proceed with the next compartment, which is, let me open a new topic. And while I'm typing the topic, you will understand what it corresponds to. Predictive coding. All right. So we will start with this one. The predictive coding uses a little bit more of random signal processing tools and characteristics as opposed to the other techniques that we have seen for lossless compression, which just use probabilities, simple probabilities, right? Because we are taking a look at the histogram and sorting according to the cumulative probabilities and all those things. That was simple. But starting from the predictive coding and continuing with the quantization and transformation and all those things, we will be needing a little bit of more random signal processing. And since it's a mandatory course for a majority of the telecommunications major students, I'm pretty much sure you are already covering many advanced topics of random processes, but I will also indicate a few things, which can be titled as random processes. Of course, it's not a lecture of random processes. I'm just writing some small portion of it. The first thing that I would like you to remember is the expected value. This is the notation of the expected value of a random process x of t, and it is a time varying random process. By the way, there seems to be some construction going on in the building, obviously. Are you hearing the noise of that construction? I am hearing it, and I just hope that you don't hear it as much as I do because of the microphone, hopefully. This is the expectation of the random process of x of t, and it generates a time varying expectation. Because x of t is a time varying signal, it is just a random signal, but it doesn't have to be stationary. If it is stationary, for the stationary thing, so let me say it like this: if it is stationary, then expectation of x of t becomes expectation of x, which can be represented as the mean of x, of course. And that is by definition obtained as the integral, you have to remember these formulas as well, of the random variable x times the probability density function f of x times dx. So this is how you obtain the expected value. Now, this was the first thing. The second thing, for example, is expectation of a function of a random variable. Let's not go into the details of the function of a random process. Let's not make it time varying. Let's make it stationary. This expectation is, it can be achieved by saying that y is equal to g of x. Okay. And then you take a look at the mean of, or the expectation of y, which is integral of y times probability density function of y dy. But interestingly, it is the same as this. Y, which is g of x, integral of y time, it's not g of t, excuse me, it is g of x. It's not a time function, it's a function of the variable x. For example, we are taking the square of it. So that would mean we are calculating actually the expected value of x squared. So that's the thing that I'm talking about. And then the probability density function of x instead of y, and integrate over x. Okay, so this is something that usually students just forget and they get confused. If, for example, if g of x is equal to y is equal to x squared, the students usually try to find this integral for the expected value of y. But the probability density function, the determination of the probability density function is not very easy. It requires convolutions and things like that. And at that point, many of the students just, stop because it becomes too difficult. However, as you see, it's easy. The determination of the expected value is not as complicated as it seems. The third thing that I want to mention is the linearity of the expected value operator, because it uses just an integration. And because of the linearity, usually it can be, the expectation operator can be interchanged with other linear operators like this. For example, this one is actually equal to a times expected value of g of x plus b times expected value of h of x. Or if you are having the expected value of an integral, so expected value of an integral of f of x dx is essentially equal to integral of the expected value of f of x dx. So it's a linear operator. It can be interchanged. The order can be interchanged among other linear operators as well. This is something that I want to emphasize. Now, the next thing that is of critical importance is independence and uncorrelatedness. Okay, let me write this: independence and uncorrelated correlatedness. All right. So what is independence and what is uncorrelatedness? First, I will start with this inequality. Expected value of g of x times h of x is certainly, not certainly, but I mean, in general, as a formula, is not equal to expected value of g of x times expected value of h of x. These two are not equal. Okay. Look at here. But they become, this becomes an equality. Equality like expected value gx times hx becomes really expected value of gx times expected value of h of x if g of x and h of x are statistically independent. H of x and g of x are statistically independent. So this is the definition of independence. If they are independent, their multiplication does not cause any complexity in the expected value. Expected value of the multiplication is the multiplication of the expected values. That is the statistical independence formula. Uncorrelatedness is a different thing. If h of x and g of x are uncorrelated, then expected value of g of x times h of x becomes 0. If it is 0, then it means uncorrelated. If the multiplication expected value, it means that their cross correlation, expectation of g of x times h of x is the cross correlation of g of x and h of x. And if their cross correlation is nothing, it means they are not correlated. They have no correlation. Okay. This happens. Independence and uncorrelatedness correspond to the same thing sometimes, and that sometime is when they are independent and they have zero mean. So if two processes are independent and they are zero mean, then they are also uncorrelated. And automatically you see it from these formulas. But let me write it. If h of x and g of x are independent and zero mean, that means they are uncorrelated. But not the other way around. They may be uncorrelated without being independent and zero mean, but their multiplication expectation will still give you 0. It means they're just uncorrelated. So one of them does not imply the other one. Independence doesn't mean uncorrelatedness. Uncorrelatedness doesn't mean independence, except for the Gaussian process, as you may remember from the probability theory. Since we are talking about uncorrelatedness, the correlation with itself is known as the autocorrelation. Let's remember what an autocorrelation means. It's an entity that is computed for a single function, random function of x of t at two time instances, t1 and t2. So what is the correlation of x of t between its value at t1 and its value at t2? And that is this correlation. It's like a cross correlation, but it's actually the cross correlation of the same signal that you evaluate, one for its value at t1, the other one for its value at t2. When you think of it, when you think of autocorrelation in this kind of a formula, it is for many practical purposes not as useful as the autocorrelation of so-called wide-band stationary processes. So if x of t is wide-band stationary, by the way, the thing that I'm going to write for the formula of the autocorrelation is the condition for the process being wide-band stationary. Wide-band stationary means it is stationary in its mean, so its mean doesn't change. Expectation of x of t is mu, and so two things we have. Expectation of x of t is mu sub x, so it's not varying with time, and the autocorrelation only depends on the time difference between t2 and t1, which can be represented as Rx of tau, where tau is, let's say, t2 minus t1. Which can also be obtained then as an expected value of x of t and its tau shifted version, which is x of t minus tau, like this. So if these two conditions are satisfied, then it means x of t is a wide-band stationary. it means it is stationary for the mean and for which is the first moment in probability, and its second moment, which corresponds to the correlation or autocorrelation, which induces the entity or the concept of variance. So if you are talking about the mean and the variance, but not higher order, third or fourth or fifth, whatever order, higher order cumulants, then it means it's wide sense stationary process. For the wide sense stationary process, we further have a few definitions. For example, Rx of 0 would correspond to expectation of x square of t, because tau is 0. X of t times x of t is what you have, which is the mean squared power. So you measure the power by looking at the value of autocorrelation at its 0 value, which typically corresponds to the peak, of course, because we cannot have any other Rx of tau that can be greater than Rx of 0. Rx of 0 is the peak value. It can later become the same as Rx of 0. For example, for tau is equal to 5, it may be equal to Rx of 0. There's an equality. It's less than or equal to. It usually, such things may happen when there is an oscillation. If it's an oscillatory signal, right? Then, of course, if you consider a sine wave is most matching to its own 0 shift, and after shifting with the same with an amount corresponding to the period, after one period it becomes the same, so it matches again perfectly. That's what we mean by that kind of a signal. The variance, which is notated as sigma sub x square, is equal to expectation of x square t, which is the mean squared power, minus the square of expectation of x of t. So it's actually Rx of 0 minus mu x square. This is the variance. So the variance and the mean squared power are different entities, particularly if the mean is not equal to 0. If the mean is equal to 0, for 0 mean sequences, Rx of 0 and the variance become the same. Usually, we measure the compressibility, predictability, transformability of signals in terms of their variances, not in terms of their signal powers. We don't look at the autocorrelation. We look at that because we usually assume that we remove the mean of the signal from the signal first. So we artificially make it 0 mean, and then we work out the correlations and all those things. So the variance, which corresponds to the variation from the mean, so how much it deviates or varies with respect to the mean value on the average, that is a measurement of variance. That's what variance means. And so if you remove the mean from the signal and make it 0 mean, then the power of the signal will automatically correspond to the variance. And that's what we will be dealing with. The cross correlation is another thing that we may be interested in. And I will only give a definition with respect to stationary, wide sense stationary signals, X and Y. And inside the expectation, we put X of t and Y of t minus tau. And this cross correlation is a very fruitful, useful tool to see how much two signals are correlated within each other within a shift, of course. So for example, in signal detection in telecommunications, if some signal is coming, we usually slide it over some known signals and look at which one it matches best. So the matching criteria for signal detection is usually performed by cross correlation. In cross correlation, we cannot say that var ix of 0 is the greatest, because one signal can be a rectangular box starting from 0, and the other signal may be a rectangular box starting from 1. So we must shift one of them to the other one to make a perfect match. So it's we don't have this property, of course, for cross correlation, because we have now two different signals. And there is one, first let me put an end to the layout and mention about one thing. If you have x of t with mu x, and if you obtain y of t, which is x of t minus mu x, which means the operation that I was telling you, removal of the mean, it becomes a zero mean, then the autocorrelation of the zero mean function becomes the so-called autocovariance of x. So the difference between autocorrelation and autocovariance is that for calculation of autocovariance, you have to remove the mean and make it zero mean. And afterwards, you calculate the autocorrelation, and it becomes the so-called autocovariance, which is, as I say, usually the thing that we use. We use autocovariance for our calculation purposes. We look at that one. It shows us for multidimensional random vectors what is the direction of the variation, which is higher in variation, which will be noted as the principal component analysis. So autocovariance is the thing. If you move the layout of covariance into a starting position, if you move the shape to another position, instead of a zero center, move it to another centered position, that is usually the autocorrelation that we're talking about. And we do not really make analysis of that one. Nevertheless, here in this part, I'm more dealing with the autocorrelation because it has one significant relation with the harmonic analysis, that is the Fourier transform. If you take the Fourier transform of Rx of tau, tau is like the time, t, right? So Rx of tau is like a time signal, where time is replaced by the time difference, which is tau, but it's a function, and you can take the Fourier transform of that function. What you get is so-called the power spectral density. I will put two x's down here of f, sxx of f. That is the Fourier transform of the autocorrelation. And this spectral density, or power spectral density, has a lot of practical uses, and it's very important. Again, you may be seeing some other courses related to detection and estimation theory and such things, where or random signals, where again you hear of these power spectral density operators. But power spectral density is the only Fourier transform domain entity that we have for random signals. For random signals, x of t, in other words, we don't really have x of t. We cannot write it as x of t, because when we say x of t, it looks like it's a deterministic signal, but we don't have it. It's just a random function. So Since we don't have x of t, we cannot take the Fourier transform of x of t, which is capital X of f, for instance. We cannot talk about it. We don't have it. The only Fourier transform that we may have is the Fourier transform, its autocorrelation, which is essentially a deterministic function of tau. So autocorrelation is no, it's deterministic. Therefore, we can take the Fourier transform of it. And where do we use it? We use it for filtering, for instance. If, for example, x of t rolls into a system, a linear and time invariant system, then the output is y of t. Suppose that both x of t and y of t are random signals. So it's quite inappropriate to write it like this. Since input is random, the output is also random. How can we relate y of t to x of t? Normally, if it is a deterministic signal, then we convolve x of t and h of t and obtain y of t. Or we take the Fourier transform of x of t and say it's capital X of f. We take the Fourier transform of h of t and say that is capital H of f. Then we multiply x of f and h of f and obtain y of f, the Fourier transform of y of t. But it only works if things are deterministic. These are random, so we cannot do that. Instead, what we do is we say the following. The power spectral density of the output is equal to the power spectral density of the input times the Fourier transform of h of t, which is the frequency response, magnitude squared. It's not very difficult to obtain this formula, and it is a very nice take-home exam question again to try to show this. And these are usually not in the compression books. These are more signal processing or telecommunications like things. Even in the book by Simon Haken or Proakis, which are telecommunications books, you will be the derivation of this formula. Writing it in the Fourier domain is way easier than writing it in the tau domain or time domain in terms of the autocorrelations. But I will also try to write it down. If you take the inverse Fourier transform of this expression, you will have Ry of tau to be equal to multiplication with h of f and multiplication with h conjugate of f of sx of f. So there are two multiplications corresponding to 2 times convolution. So it's a double convolution. So one integral for the first convolution, one for the other, both from minus infinity to infinity. And we have, for the first one, we have h of tau 1. And for the second one, we have h of tau 2, which comes from, one of them comes from h of f, the other one comes from h conjugate of f. And we have Rx of t minus tau in the convolution, if you think of it like that. Like, but I will not use t because for autocorrelations we are using tau. So it's a little bit confusing and disturbing. It's complicated a little bit. Tau minus tau 1 minus tau 2. So I'm convolving Rx of tau with h of tau and with h of tau again. You can think of it like that. D tau 1, D tau 2. All right. So these two equations gives you the what is happening in the frequency domain and in the time-like domain, time difference domain. Clearly, the frequency domain representation is way easier to interpret, to remember and to interpret. The interpretation is as follows, by the way. The power spectral densities are always positive. Let's write it. Sxx of f is always positive for all frequencies. So you cannot have some negative power spectral densities because an integral from a certain frequency to another certain frequency, it may be from minus infinity to infinity, 2 of Sxx of f df is the power of the signal. So if you integrate the density, you get itself. That is, if you integrate the power spectral density, you get the power. If you integrate the power spectral density over the spectrum, over all the spectrum, you get the power. And power is a square term. We know that power cannot be negative. Mathematically, it is always positive. And this is a critical observation. And it also shows that if, since the power spectral density is always positive, this one, when you multiply it with h of f magnitude square, and magnitude squares are also positive terms in terms of mathematical expressions, multiplication of a positive term and another positive term will give you a positive term. So syy of f is, of course, then naturally positive as well. While I was teaching the telecommunications in the undergraduate, once I asked this question to the undergraduates. I don't know if you have encountered this question in your telecommunications course. Maybe you have already encountered it and you know the answer. But even if you haven't, please think of it from this perspective and try to answer. I give the students this autocorrelation function. From -1 to 1, it's a constant value. Let's say it 1. So can this be an autocorrelation? The autocorrelation, not n, the autocorrelation of a random signal. This was the question that I asked several years ago. So now I'm asking this to you, and I'm expecting an answer from one of you guys, if you have. Any comments? Are you with me? Or did you just open the Zoom account and actually doing something else? So this is a question for you. Yes? Still listening? There is some amount of noise, but I cannot hear you if you are talking. Abdul Majid. Maybe there's a problem with his mic. That's also a good Zoom trick, by the way, to have a problem with the mic. Who else?
No, I don't have the answer.
Yeah, I see. That's a good one. That's a good response, actually, to say that I cannot think of an answer. It is much better than giving no response like your other friends, which is a pity, which is a shame for them. Anyway, the answer then for this is no, this cannot be the autocorrelation of a random signal, because when you take the Fourier transform of this Rx of tau, which is a rectangular box, it becomes the Fourier transform of a rectangle, which is, as you may remember, which is sinc, a sinc shape, okay? And it goes to negatives. As we all know, like this. So these parts go to negatives, and a power spectral density cannot be negative. So the answer to this question is no, it can't be. So you have to think of it like this. You have to think this way always. The power spectral density is always positive. And The reason that it must stay positive can be thought of like this. Suppose that you are filtering this Rx of tau, or this x of t, the function, through a bandpass filter. The bandpass filter is, let's assume, passing this band, deliberately chosen to be like this, these frequencies. If it passes, then through these, we know that the equation is, the power spectral density is multiplied by the square magnitude of the filter, and the square magnitude square of these rectangular shapes are again the same rectangular shapes because they are already positive, and if the peak value is 1, its square is also 1, whatever. So when we multiply these rectangular boxes with Sx of f, you will only have these negative parts. They will pass from the filter, and everything else will be annihilated. They will be gone. And then that becomes the power spectral density of the output, SYY of F, purely negative. And then when you integrate SYY of F to find the power of Y, power of Y, it will be negative. And that is not possible. That's why you have to always have a power spectral density that is strictly positive. By the way, the second part of the question was, can you think of an Rxx of tau shape? Since this one cannot be the power spectral density, you cannot have this kind of an autocorrelation function. Can you think of an autocorrelation function which is properly fine? And again, I'm asking you this as the follow-up question, as I asked this to undergraduate students. It's not this rectangular box. This one certainly doesn't work. Can you think of a simple Rx tau function which works? And this indicates the necessity of the knowledge of signals and systems as an prerequisite, if you wish to say, for this course. That's a necessary condition, because the answer to this question is, there are several answers, of course. One of the easiest answers is this example of an autocorrelation, which is like this. Let's say from -1 to 1 to the peak of 1 Rxx of tau. Let me make these two from -2 to 2 on the tau axis. The Fourier transform of this triangular shape, if you may remember, is equal to sinc square. The Fourier transform is equal to sinc square. And that is certainly positive. Sinc goes to negatives, but sinc square always stays at the top of the horizontal axis, remaining positive. Why is it sinc square? Because this shape is the convolution of this rectangular box and the same rectangular box. If you convolve two rectangular boxes, they will generate a triangle. So the Fourier transform of this one is sinc, and the Fourier transform of this one is sinc. If you convolve in the time domain, then you multiply in the frequency domain, which makes sinc square. Okay, that's how things work. Anyway, This was a long introduction, but I hope that it would be beneficial for you to have an understanding about some fundamental concepts of random signals, because right now, after the break, we will be starting the predictive coding, as the title suggests. Let's take a look at the title. Uh, no, it's not visible here, but if you look at here, as you see, it says predictive coding. Now we are covering the predictive coding. So making a prediction is the strategy that we will be doing. But these fundamental flavors of random signals is necessary for the generation of optimum predictive filters, and they will also be necessary for optimizing quantizers, which is a further topic that we will soon see in the coming weeks. So this was that kind of an essential introduction. It was not related to predictive coding yet. We will be starting the predictive coding after a break. Let's now give a break. It's 10:30. Let's meet at 11 o'clock sharp, okay? And we will continue with our discussion. So we give half an hour of break right now. I'm stopping the recording, and after that I'm leaving the meeting. Please have your questions in your minds, get them ready, prepare the questions, and when we start the next lecture, you may ask them if you have any. Okay, so now I'm stopping the recording and ending the meeting. See you.